Now, Jeff Hawkins was the co-founder of Palm Pilot. Anybody remember Palm Pilots? Okay, a few people do, good. So Palm Pilots were before the days of smartphones, when you wanted to have something that would have your diary, it would have documents, it would have the ability to even play games. So it was kind of separate from your phone. And what Jeff did was he created the Palm Pilot. Palm Pilot was very popular sort of 20 years ago, I guess it was 20 years ago. And what he did was he looked at how people interact with that machine. And one of the things that he didn't want was a keyboard. So he wanted a stylus that would be able to let people enter text. Back in those days, your typical Palm Pilot had about 8 megabytes of memory, and it had a very slow processor compared to today's machines. So what he did was he came up with an idea which was called graffiti. And graffiti is a simplified way of entering text with a stylus. The idea is that you only have to use one stroke of the stylus for every character. So it took a little bit of learning how to do, but it was very, very successful. I remember using graffiti, and I got very quick at entering text with that. So having been successful with the Palm Pilot, he made a lot of money. He cashed out. There was an IPO. And he was then able to go off and explore some of the things that he really wanted to do. And one of those things was artificial intelligence. And he ended up writing this book. He created another company that is working on using these technologies in terms of building software products. And the approach that he took was to look at how the human brain works and then use that as a way to create a model in terms of the software so that he could, in theory, replicate what our brains do. We will talk a little bit now about some neurology. Not much, but just a little bit to give you an idea of where these theories and ideas came from. So this is a picture of your brain. And your brain has this structure which has lots of different pieces to it. But the important bit from the point of view of what Jeff did was looking at a thing called the neocortex. And the neocortex is really what makes you, you. It's like what you think about when you're inside your head. And the neocortex is actually wrapped all the way around the outside of your brain. So it's the outer layer of your brain. And we can look at that in a different way using a stack of my business cards. So you might immediately think, well, how can you use a stack of Simon's business cards to represent part of my brain? But the thing is that there are 6 layers in the neocortex, 6 layers of neurons which interact with each other as different layers. And each of the layers is about the thickness of a business card. So if you put 6 business cards together, you're looking at the thickness of the neocortex in your brain. What Jeff did in terms of his sort of studies and looking at how to model this was he came up with what's called the hierarchical temporal memory. And this was a framework in software about how you could make a software system that worked in roughly the same way as your human brain does. So it uses the idea of neurons. These are cells which are in your brain. Neurons connect to one another using synapses. And the way that your brain works is by putting information in, and then it feeds through the neurons. The neurons connect to each other through these synapses and send signals. As you learn things, the signals that become used more frequently develop stronger connections. So there's a way of developing connections between neurons that gives you the ability to, in effect, remember what you've done that's successful and eliminate things that weren't successful. So you build up these relationships between the neurons. The other thing that you have in terms of how that works, and this is something which is a little bit different to the way that most machine learning and deep learning algorithms work, is the concept of time. So in addition to saying, okay, we put data in, we learn how to recognize picture, we learn how to do something, and then leave it alone. What the hierarchical temporal memory model says is that you also include time. So you keep feeding data in, and as connections become less used, they decay over time. So it adds in this element of time so that you lose the connections as they become less used. So it's not a fixed set of data, a fixed set of connections, and that's quite important. And it potentially leads to a much better way of having a system that learns. Let's talk a bit about machine learning and the whole basics of how artificial intelligence works today. Now, this particular cartoon has been around for a long time. I remember seeing this when I was first starting to learn how to program. And there's a couple of ants there. You probably can't actually read this, but a couple of ants there, and they've got this flow diagram of their software. And in the middle there, he's pointing and it says, "Then a miracle occurs." And at the bottom he says, "Good work, but I think we might just need a little bit more detail here." And this, to me, is very much how machine learning works. It's like a miracle. There's this software that does things, and suddenly you get this ability for cars to drive themselves, for pictures to be recognized, all the things that we're seeing today. How does that actually work in practice? Well, as I said, there are different ways that you can represent artificial intelligence in the things that we do today. First of these is what we call machine learning. Machine learning it's about giving computers the ability to learn without being explicitly programmed. Now, we're all familiar with software development. Software development is basically creating a set of instructions. A set of instructions which you give to the computer, data comes in, the computer follows that set of instructions, something comes out as a result. So it's a fixed way of processing that data. Now, machine learning is more about adapting to the data so that the way that it's processed changes without the programmer having to explicitly change the set of instructions. So those instructions are dynamic, they change over time. The key thing with machine learning is that we need some way of training it. We need a set of data to provide as a way of saying, these are typical inputs with typical outputs. And we'll use that to train the system so that when you give it a different input, it's able to recognize it, it's able to generate an output. Now, we can look at that in a simple form using a graph. So in our graph here, we've got two dimensions, x and y. But typical machine learning problems have lots of dimensions. So the dimensions, in effect, represent the different pieces of data that you have. Not the individual values, but the different variables that you have associated with a particular piece of data. So in this, we're just going to use two dimensions because it's easiest to look at what we're doing here. Now, what we've got is a set of training data, which are the points on the graph. And what we need to do is come up with some mathematical function which allows us to say, if we get a new value, and we put that in and say the x value, give us the equivalent y value. And we need that to fit in terms of the training data that we've got. The simplest way of doing that is just a linear graph. So we have a straight line which we try to fit as best as possible between the points that we've got. And if we look at that as humans, we can see that that line fits pretty well. Not all the points are on the line, so there's a certain error that we'll get. But if we were to put in an x value, we would get out a y value that looks like it would be pretty reasonable based on that training set of data. In terms of training data, the way that you can use it is in a number of different ways. So the bigger the set of training data you have, obviously the better you're going to be able to model the way that you want to predict things in the future. But you can also take your training data and divide it up. So you take, let's say, 3/4 of your training data, you train your model, and then you use the remaining quarter as a way of testing whether that model actually works. And then you can refine your model based on that. You can also then swap around and say, okay, let's take the first quarter of the data to be our testing data, take the last 3/4 and use that as our training data, and do that iteratively and refine your model. Obviously, if we look at this graph, we could say to ourselves, well, actually, we could do better than that. We could do better than that by using a curve. So we could, rather than having a linear function, we could have a polynomial function. And we could say, right, let's have a better fitting line through that data. The problem you have is trying to avoid going too far. Because what you can do is what's called overfitting. Overfitting is, in this case, where what we said is, right, let's create a polynomial that goes through every single point on our graph. That way we know that we would have an accurate prediction for every point that we have in our training data set. But if we look at that as a human, we'll see that that's probably not the best graph to use. Because if we had a value very near the origin of the axes, and we put a value in there, what we're going to get is a very high value because our polynomial goes way up, but that's probably not going to be an accurate prediction based on our training data. So what we need to do is figure out how to find a value of the graph which is somewhere between overfitting and underfitting. And that's the tricky bit in terms of doing this. Now, the next thing is what's called deep machine learning. So machine learning is where we take training data, we have labeled data, so we know what the x value is, what the y value is, and we try and find a way of predicting things in the future. Deep machine learning is much more about using neural networks and about having unsupervised learning. So unsupervised learning still has training data, but the data is not labeled. So what the algorithm has to do is it has to learn from the data how to classify that data. This is obviously making things more complicated because it's not simply a case of putting in obvious data and being able to predict results. So what we do in terms of deep machine learning is use a neural network. We group together sets of neurons. This is based on the idea of how the brain works. So we have these neurons that do something, they connect to other neurons and allow us to process data. It's very much about non-linear processing. So we're dealing with lots of neurons, we're dealing with different configurations of those neurons and how we actually go about using them. The other thing is that by putting these neurons into layers, in the same way that the human brain does, we can have different abstractions of the problem in the different layers. And by that I mean that, let's say we take a photograph of something. We can represent that as a set of pixels. We can represent each pixel as a set of values of the primary colors. We put that in as input to our top layer of our neural network, and its representation is an array of pixels. The next abstraction that we can get from the next layer would be, say, identifying the edges in that image. That's a different abstraction. We can then pass that into another layer. We can do some other processing of that and get another abstraction from that, saying, okay, from those edges we can start recognizing a shape, and then pass it to another layer with the idea that when we get to the output layer, what we have is a classification in terms of what's in that picture. So we start off with a set of pixels, we go through the abstractions, and at the end we see that it's a cat or a dog. This is also a good analogy in terms of the hierarchical temporal model. You can build in the time basis to it. You can put in the ability to decay the links between neurons if you want to. So if we look at the structure of how our neural network works, we have a set of nodes. And the nodes are the neurons. Each of those will have connections from other neurons. So those are the inputs that are coming to our neuron. Each input is modified as it comes in by a weighting value. So it gets multiplied by a factor to determine how important the value that's coming from that neuron is. And this is how we can build up strengths in terms of a connection. So as something becomes more of a useful connection, the weighting value goes up. As something is identified as not so useful a connection, then we can reduce the weighting. We take all of those inputs, multiply by the weighting values, and then we pass them into the neuron, which processes it through a function. Now that function could be just adding them up, it could be taking an average, it could be something more complex. But it will do some sort of basic processing on the inputs and generate an output. And that output will then be passed to other neurons, or it will become part of the overall output of our neural network. We can then link lots of these neurons together. Again, this is what we do in our brain. So we start at the bottom with our input layer. We pass in the inputs. In the case of a picture, these will be our pixels with our RGB values. And those will be processed in some way by the neuron and passed on to the next layer. The idea is that you have an input layer and an output layer, and then between that you can have a number of layers to do the processing and generate different layers of abstraction. In terms of how the connections work, for most neural networks, what you have is only connections from one layer to another. So you don't connect between neurons in the same layer. So you have connections from the input layer to the hidden layer to the output layer. The other thing is, in this particular example, we only have a forward-passing neural network. You can have ones with what's called back propagation. Back propagation is where values from the lower layers, if you like, can be passed back as a way of having feedback in terms of how the process is working. So there's lots of different ways that we can use these things, and we can configure them to handle lots of different types of problems. Taking that one step further is what's called deep reinforcement learning. And deep reinforcement learning is much more how we as humans work. So when we're born, obviously we have a brain, and we don't have this nice set of training data that is provided to us that enables us to become an instant, ready to do everything human. No, we have to learn everything. And certainly, you know, my son at the moment, he's 11, you know, he goes to school and he says, why do I have to go to school? It's like, you've got to learn. So, you know, this is the way that we do these things. And a lot of what we do is by trial and error. We try something, maybe it works, great, we remember that. If it doesn't work, we remember that. So the idea is that as humans, we learn by our mistakes. So deep reinforcement learning is much more about that. We don't have a set of training data. We basically configure the deep reinforcement learning system and then provide it with a set of inputs and let it learn from those. How we do that is done in a couple of different ways. Most common, or one of the most common, is what's called a Markov decision process. And a Markov decision process is, in essence, a mathematical model of how we make decisions. And the way that it works is it has 5 values associated with it in terms of each piece of the decision process. So there is a state. A state is something which represents where we are at a particular point in time in terms of what we're trying to do. Now, we're talking about Minecraft, so we could represent a state as being a position in the game. So that's our state, is where we are in the game. Or we could represent our state as being our health. You know, are we alive? Are we dead? Are we sustaining damage? That type of thing. We then have an action, or a set of actions. And actions are things that we can do from that state to move to another state. So we take an action, and it moves us to a different state. Again, using Minecraft, we could say, okay, our state is being at a particular position. We want to move. It takes us to a new state, which is a different position in the game. We have a probability associated with that action, which is the probability that that action will take us to a particular new state. And we can use those probabilities to help us make a decision. Because if the probability is higher of going to a new state, and that state is what we want to go to, then we might want to take that particular action rather than another one. In order to determine how successful we're being, we need a reward. So we need a reward to say, okay, if we transition from this state to this state, if it's a good thing to do, we get a positive reward. If it's a bad thing to do, we get a negative reward. And that way we can use that value to determine which of the actions we want to take. And then we've also got a thing called a discount factor. The discount factor is because if you only look at the next state, you can miss a lot of useful information. So a good example of that is if your system is designed to try and climb a mountain, what you might look at is the next state saying, okay, does the next state take us higher on the mountain? So the reward is if you go higher, good. If you go lower, bad. But what might be the case is that in order to go higher, you actually need to go lower first. So you need to go down a particular path in order to go up a different path, which takes you higher. So the long-term reward is that you go higher, but the short-term situation is that you need to go lower in order to do that. So you have a discount factor which allows you to factor in whether the long-term reward is better than the short-term reward. If we look at that in terms of a graph, so this is just representing the same thing, what we have are 3 green states, and then we have actions that can be taken from those states, and there are probabilities associated with each of those actions as to which state you will be in as a result of taking that action. So if you look at S0 at the top left-hand corner, there's an action 0 which has a 50-50 probability of either going back to state 0 or going to state 1. And clearly there's different probabilities associated with different actions. The little squiggly arrows are the rewards that you get based on something that you do in terms of that decision process. So this is the kind of thing that we're looking at in terms of using this information to figure out how to play a game. The other thing that's been quite noticeable recently, coming back to this reinforcement learning, was a project that was done actually about 3 years ago now by DeepMind. DeepMind was a company that's in the UK, acquired by Google, and they set up a very nice demonstration of reinforcement learning using a different decision process. So it uses a deep Q network, where they got the game, or sorry, the artificial intelligence system to play Atari video games. But they didn't get any information about how to play those games. All they did was they set up the deep reinforcement learning system, deep Q system, with video frames. So it had as input video frames. Obviously, these are 2-dimensional video games, so it's nice and easy to process. Fairly low resolution, so there's not too much data to deal with. And they gave it the ability to take actions, so it could control the game, so keyboard emulation to move a particular part of the game in a particular way. And they gave it a reward, which was the details about what the score was. And the goal was obviously to get as high a score as possible. What was remarkable was that they were able to get this system to learn how to play an Atari video game. So in this case, it was Breakout. The game learned that by moving the paddle in a particular way, so it intercepted the ball as it was coming down, that would bounce the ball back and it would get a higher score. So rapidly learned that by moving the paddle back and forth and intercepting the ball, it could then get a higher score. What was really interesting, though, was it wasn't just one game. They gave it about 20 different games, and each game being different, it was still able to learn based on the score and just being able to control the keyboard, how to play lots of different games. That was a really interesting demonstration of what deep reinforcement learning can actually do to learn how to play games. Right, so in terms of my project, we talked about the background and some of the details of machine learning and so on. Talk about the project itself. So the first thing was to use hardware. And I could have just used my laptop, but I thought, no, I want to involve some hardware as well. So I thought, right, I'll use the Raspberry Pi. So who's got a Raspberry Pi? Okay, quite a few people. I'm sure you've all heard of the Raspberry Pi because it's been around for quite a long time now. Raspberry Pi has been a fantastically successful development board. It really changed the game, if you like, of being able to develop embedded applications. Along came this board that was $25, yet it had a 32-bit processor, it had between half a gigabyte and a gigabyte of memory, it had lots of pins on it that you could connect things to, GPIO, I2C, SPI, UART, all those sorts of things. And so it was really easy to use this to build devices. You could connect sensors, you could connect controllers to it, you could monitor things, you could run it as a desktop. I mean, that was the other thing you could do. You could connect it via HDMI, $25. I have to think back to my first computer, which was, and I wonder if anybody in the audience, a TRS-80. Anybody remember the TRS-80? Ah, a few old hands are here. It had 16 kilobytes of memory, and it cost, in 1987, I think it was, about nearly €1,000. So think about that, 16 kilobytes for €1,000 and $25 for a gigabyte of memory. To make that even crazier, they then came out with the Pi Zero. The Pi Zero is a kind of stripped down board which doesn't have the Ethernet connection, still has HDMI, but it's only $5. 32-bit processor with 512 megabytes of memory, and it's only $5. That's just insane that you can get this kind of processing power. So Raspberry Pi, very, very successful. They sold lots of them. They literally sold millions of these things by now. Now, in terms of variations, there's been a variety of these boards over the last few years. Started out with the Model A, using an ARMv6 processor, single core, half a gigabyte of memory, some USB ports. Model B is the current one. This started out with a single core processor, but now has a quad core processor. It's all ARM-based. Quad core processor, it's actually using ARMv8, so in theory they can do 64-bit, although the Raspberry Pi Foundation are not doing 64-bit builds yet, they're doing 32-bit still. Comes with a gigabyte of memory. The Pi Zero, as I say, is a slightly older chip, so it's only an ARMv6, single core, half a gigabyte of memory. What I thought is, okay, architecture-wise, I want to use one of these Raspberry Pi boards to represent each layer of my neural network, so each layer of my Neocortex. So I'll build a cluster of Raspberry Pis, connect them to my laptop, and then have them do something useful. What I did was I built my Mark I Pi cluster. And now normally for my projects I use wood. I believe that every good software project should involve woodwork. But I've recently changed, so I'm now into Perspex. Perspex is more colorful, it's actually easier to work with in some ways, so I've used Perspex to build the rack that I've put here. So I've got 4 Raspberry Pi, I think they're Model B, Model Bs they are, and then I've got one Model B, the later version on the top, which I also put an SSD on because I thought I'd need some more storage space. And I found some nice short network cables, some nice short USB cables, and a nice big power supply. They all sort of fitted together quite nicely. But then I thought, okay, well that's kind of good, but I need a slightly smaller version of this. So I came up with the Raspberry Pi Cluster Mark II, and this is the one I've actually got on the desk here. What I've done is I've used the Raspberry Pi Model B, and then I've got 4 Pi Zeros on the top. And it uses a thing called a cluster hat to mount the 4 Pi Zeros. And I found this, it's a very nice little board that enables you to put these Pi Zeros and connect them using the USB connector on there. So you don't actually have to have any network cables, you don't have to have any power cables, it's all handled directly through the USB connection. If you look at how that works in a little bit more detail, essentially what you've got is everything connected via USB, but it enables you to do it in a way that still gives you the illusion, if you like, of having network connectivity. So we've got the Raspberry Pi at the bottom there, we've got the cluster hat which has 4 ports on it, each of those is connected to the USB, and then there's a way of connecting through the GPIO ports to control the individual Raspberry Pi Zeros. So you can turn them off, you can turn them on, you can do networking through the USB port and all of those things. So in essence, it gives you a nice compact way of having a cluster of Raspberry Pis which you only need a single network connection for, you only need a single power supply for. Right, then we come to how to use Java for embedded applications, because I wanted to build a Raspberry Pi cluster, great, I needed embedded Java for that. So when we think about Java and embedded applications, why would we want to use it? Why not use C or C++? Well, one of the first things is this whole idea of write once, run anywhere, or as many people refer to it, write once, test everywhere. What this means is it's very easy to develop the code that you want to use on your laptop. You just use your IDE, you develop your Java code, create a jar file, and then you just move it to the board that you want to run it on. There's none of this porting, there's none of this tool chain that you need set up, no cross-compilation, none of that complexity. It's just Java. Generate a set of bytecodes, put it on the device. As long as you've got a JVM, it all runs quite happily. The other thing with Java is that there's this wonderful range of libraries and frameworks that people have created that you can take advantage of. So we'll talk about some of those as we go through the later section of the presentation. But there's lots of frameworks, lots of libraries you can use, which means you don't have to write everything from scratch. It makes life a whole lot easier. From an embedded point of view, although I haven't used this in the project yet, I've got some ideas about doing some interfacing with the Raspberry Pis. And there are some nice libraries, again, which allow you to do things like control the GPIO pins, the I2C, and so on. And there's libraries like Pi4J, there's the DIO library that are available, free, open source, makes it very easy. Another big factor in terms of using Java is simplified concurrency. Right from the very beginning, Java's had the idea of a thread. You can create multiple threads, you can have those running on the same JVM, you can have them working together. Java 5 gave us the concurrency utilities, so we had things like semaphores, mutexes, rewrite locks, lots of useful features. Java SE 7 introduced the fork join framework, different way of doing concurrency, take a big task, break it down into smaller tasks, have it handed to a set of threads, have those threads generate results, bring it all together, simple set of code to do that. And we've had Java 8 giving us the idea of parallel streams, again, a way of simplifying the way we do concurrency. So there's lots of different ways we can do things in Java to have the idea of our neurons modeled by different threads. And then if we need more complex things, we can use JNI to interact with native code. Now, as an Azul employee, I do have to have my obligatory marketing slide, so I'm going to talk just briefly about Zulu Java. What we do at Azul is we take OpenJDK and we compile it into binary distributions. So we do that for various different platforms. We do it for Intel, we also do it for ARM, we do it for PowerPC, we do it for ARM v6, v7, v8, hard and soft float, 64 bits now available. We're doing some interesting thing around the C1 and the C2 compilers to improve efficiency of the JIT compiled code. Very much a drop-in replacement for other JVMs. And the important thing is, one, it's free. You can download it from our website without any cost. Obviously, if you want to get support for it, we'll happily talk to you about that. And there's no licensing restrictions. It doesn't have the same field of use restriction that you have with certain other companies' JVMs that used to run on ARM. So it's an interesting project from that point of view. Like I say, it's free, but with commercial support available. End of product pitch. Right, machine learning in Java. Okay, so we've talked about what machine learning is, we've talked about deep learning, we've talked about deep reinforcement learning, talked about using Java. How do we put the two together? Well, there's this thing called DeepLearning4J, which is another nice library that's been created by people who want to make a set of tools available to you to help you build these types of applications. So DeepLearning4J is really about a toolkit for building, training, and deploying neural networks. And there's different sections to it, there's different ways of configuring it. The most important section is what's called ND4J. ND4J is all about n-dimensional arrays in Java. I talked about machine learning and how you can have a graph with 2 dimensions on it. Most machine learning applications have lots of different variables associated with each piece of data in a training set or in the data that we're working with. So you need somewhere representing those as a matrix, an n-dimensional matrix, and then you need to be able to do matrix mathematics on that, matrix manipulation. So ND4J is all about handling multi-dimensional matrix multiplication manipulation through Java. There's also a piece called DataVec. DataVec is how you take the features that you have in your data set and convert them into a vector. Now, a vector is a single dimensional, it's a single set of values in a matrix, so a single set of values. DataVec will help you transform the values you have in your data into a single vector for the manipulation through the ND4J. And then there's another piece called Arbiter, which is used to evaluate the model that you create for your machine learning, determine how effective it is, and then modify it based on feedback so that you can update things as you learn, as your system learns how to do things. And then there are these things called hyperparameters, which are the values that get determined that affect how your system works. So they're not the training data, they're the values that you create from your training data to make your model work. And again, you can optimize that in different ways. There's a thing called DeepLearning4J core classes. So there's various things you can use. There's a neural net configuration, which comes with an optimization algorithm. There's a multi-layer configuration, because you might want to create, as we've seen, a multi-layer neural network. You can have back propagation associated with that. So this is where you can pass values back from lower layers of the neural network to change the values as things are learnt. And then there's these more complex things called truncated back propagation through time that you can control as well. So this is looking at how the time value affects things. And then you've got layers, either dense layers, output layers with inputs and outputs. So these are the sort of basics that you need in terms of doing a DL4J network. There's also a nice set of things that you can have for reinforcement learning for Java. So this is part of the libraries as well. And this is what I was looking more closely at, because it sort of fits more with the Minecraft thing. So what that gives you is the ability to deal with reinforcement learning where you've got both low-dimensional and high-dimensional data. Low-dimensional data is where you only have a small number of values. You can think of that as being like state. So if you think of the Minecraft game, you know, your state is where you are, what your health is, things like that. So there's only a small number of values associated with it. High-dimensional data is where you've got a lot of values, which would be a video frame. So you've got all the pixels in that video frame that will be thousands, tens of thousands of pixels. The RL4J library provides you with a set of classes which allow you to do various things. So there's an MDP class which fits in with the Markov decision process. There's also a DQN class which allows you to do the deep Q network side of things. And then there are policies associated with how you use these. Policies are the thing that you build to determine how to decide what action to take next. So there's a variety of these which I won't go through in detail, but there's an actor-critic policy, there's a Boltzmann-Q probability distribution class, there's a DQN policy, and then there's an epsilon greedy partially random way of doing things. So there's different approaches that you can take in terms of actually having your decisions made in different ways. Because randomness is actually quite useful, as we'll see. Minecraft and Project Malmo. So who here has played Minecraft? Okay, quite a few people. Minecraft is immensely popular as a construction game. If you've got children, you probably have seen them playing Minecraft. My son is 11 years old and he absolutely loves Minecraft. He loves Minecraft, he loves modding, he loves changing things in terms of how the game works. It's incredible what you can actually do with this game. There's various different modes that it'll work in. So there's creative mode where you never die, there's survival mode where you can die, and then there's hardcore mode where you die more easily. What's really interesting about this is it's incredibly popular. There's 121 million copies sold of this in all versions, but the first version was written in Java. So it really is the most successful, certainly the most successful Java desktop app ever. Because it's incredible to see it's written in Java and it runs really well. So a couple of screenshots here. So you've got the Minecraft intro slide, and then you've got sort of worlds that you can build, and you can build fantastic worlds in this. I've seen people do all sorts of weird things in terms of building skyscrapers and cruise liners and all sorts of things that people build. And the other weird thing to me is that my son, as I say, he's mad on Minecraft. But the other thing he really likes is he likes watching other people play Minecraft on YouTube. I still haven't quite got my head around why he wants to do that, but there you go. Now, Project Malmo. Project Malmo, because the company that developed Minecraft originally, Mojang, were acquired by Microsoft. Microsoft looked at this and they thought, oh, this is quite an interesting thing from a research point of view. And Microsoft have a number of researchers who work at Cambridge. And they looked at this and they thought, this would be a really good thing to use in terms of developing machine learning, deep learning, reinforcement learning algorithms, because it's a relatively simple game in terms of what's going on. The graphics resolution is quite low, it's very chunky, it's very blocky, there's none of this heavy three-dimensional kind of graphics going on. It's really quite simple from that point of view, but very complex in other ways. So it would be really good to use that as a way of training and testing machine learning algorithms. So what they did was they created their own mod for Minecraft. And the mod allows it to interact with the game, so you can control the game, you can send it control and commands, and you can also get back information. You can either get back information in the form of video frames, or you can get back information in the form of the state of your world at that point. So it's all written, available in different languages. There is a nice Java version available as well. And if we look at some sample code for this, what you need is an agent host. So the agent host is what's going to enable you to connect to the game and to do things with it and interact with it. So you create an agent host, then you need a client pool, and you can connect to the client pool through an IP address. This was immediately the thing that I looked at and go, oh, good, because I can run my brain on my cluster, and then I can run Minecraft on my laptop and have the brain communicate to the IP address of my laptop. So that was good. Then you need a thing called a mission specification. And the mission specification sets up what the agent is actually going to do in the game in terms of its configuration. So there's various things you can set, like how long you want the game to run for. You can set the resolution of the video if you want. There's other things you can do as well. Then you can record all the information about what happens during the play of the game. And that's very good because if you want to analyze afterwards how your agent worked, then you obviously need to be able to look at the sort of log of what happened. So you can set it up to record everything into a file, you can record all the commands, you can even record a video of the game as it's being played so you can watch it again and again, or your son can watch it again and again. You can record all the rewards that you get, you can record all the observations. And then once you've got all this, you can actually start your mission using the various things that you've set up, and off it will go and it will play the game. In terms of interaction, you use the mission specification, so you can things like set the mode to creative or leave it as survival. You can do various things in terms of setting up the world that you want to work in, and I'll show you that in the demo. So you can place different blocks in different positions, you can put the agent at a particular start position, you can have a predefined world, so that rather than getting a new world every time, you can have it play in the same world every time to learn things as it goes through. The agent host is how you actually work with the game. So you start the mission, you can send commands, you can say move forward, turn left, turn right, drop, interact, pick up, all those types of things. And you can look at the peek at the world state, so you can get what the state of your world is at any point in time. Putting it all together, right, so this was taking the architecture that I had before and then sort of fitting it into what I have in terms of my cluster. So I used the Raspberry Pi 3 as really the kind of demo controller. That was the thing that was going to send the commands to the Minecraft game, get the information back from the Minecraft game. Having got that information, it was basically providing that to the input layer, and that was really as a set of rewards from our Markov decision process. That used the reinforcement learning for Java, passed it through a number of layers to abstract out the information and determine what to do next, and then pass back an action. So this is again the Markov decision process, using the rewards, generating an action. Action would then be passed to the game, we play the game. Demo scenario. So originally I thought, right, what do I want my game to do? Or my agent to do? And I thought, right, I'll have it build a house. Great, have it build a house. Turns out that's really hard. Really hard, so no, we won't do that. Okay. So I thought, right, let's revise that. Let's have the agent build a wall. Just a wall, no house, just a wall. Yeah, turns out that's simpler, but still really hard. So we won't do that either. So I came up with the demo revision 2, which is have my agent walk around in the game and avoid dying. That seemed to be like a relatively simple thing. It's this binary situation, alive or dead. And you can set up like an obstacle course where what I've done is put lava blocks around the game, and then have the agent walk around and try to learn to avoid the lava blocks, because the lava blocks kill it. Okay. In terms of like applying the machine learning to Minecraft, the tricky bit is actually translating the Minecraft data into the machine learning, DeepLearning4J system. So it's a lot of figuring out vectors in terms of creating vectors of the variables that you've got, and putting it into the machine learning algorithms and then actually having it do stuff. So what I'm doing at the moment is I'm using the world state rather than the video frames. The long-term goal for this project is to actually use video frames, get the system itself to determine the information from that rather than having it kind of handed to it, and do that. Starts off with random moves, and then the idea is that it starts random, learns what it needs to learn, and then becomes more successful over time. Use reinforcement learning, hopefully, to learn how to navigate the world safely. Right, conclusions and future directions. So conclusion-wise, what I learned from this was that embedded hardware can be applied to machine learning, deep learning. You know, it's not a huge system in terms of the number of neurons and things like that, but what I found is that even with the Raspberry Pi Zero, with the amount of memory you've got, neurons are quite simple, they don't require a lot of storage, they don't require a lot of processing power, so you can actually run a reasonable number of neurons on a Raspberry Pi Zero without actually exhausting the resources. It's a good way to model the way the human brain works. Java, I found, is an ideal language for this. Obviously, it's easy to learn. The simple threading model makes life easy as well, and the availability of libraries is very good. And Minecraft is definitely a fun tool to use for testing of this. Things I want to do in the future, more work obviously on just the machine learning side of things, making the algorithm better, make it play better. I'm interested to look at what's called JCUDA. This is the idea of using GPUs rather than CPUs. And I've actually bought myself a thing called an NVIDIA Jetson TK1 board, which is essentially a video graphics card, but in a sort of PC format, so that you can get access to the GPUs and use those to process the neurons rather than having the CPU do it. And that will be interesting. The other thing is, as I say, using video frames and then processing on that, and that's probably going to use some of the OpenCV libraries that are available for that. Further information, raspberrypi.org, obviously clusterhat.com is where I got my information about my cluster hat, deeplearning4j.org, minecraft.net. This is the rather long URL for the Malmo project, so you can download that from there. And as I say, Zulu.org is where we provide our free version of Java. I will put the code up on GitHub at some point. Still needs a bit of tidying up, a little bit more work required, but I will be putting it up on GitHub. I'll tweet about it when I actually get it up and put it there. So, demo time. Okay. Like I say, deep breath in and lower your expectations. Right. So I have Minecraft running already. And then what I'm going to do is, so I've pre-set up, warmed up the, well, not warmed up, but started up all the different Pis. So essentially, like I say, what it's going to do is it's going to take the information from the game, it's going to pass it to the set of Pis, pass it through the different layers, and use some randomness, and then hopefully use some intelligence to make decisions and play the game. There we go. Right. So if we then, so it starts up, needs to build the terrain, and then we'll see. There we go. Right. So eventually, yes. Let's put that up. Right. So what it's doing now is moving around. Yeah, it's not really easy to see on here, but so it's moving around, and you vaguely see. Yeah, there we go. So there's some lava blocks there. At the moment, it sometimes gets a bit lost, because I haven't put too many lava blocks into the game. So it sometimes gets a bit and goes off in a completely different direction. But this is part of the fun of it, is that it just goes off in a complete. Yeah, see, it survived by walking in completely the opposite direction. Somebody said to me when I ran this, they said, "Well, wouldn't a valid situation be that the game just decides to stay exactly where it is?" And I said, "Yes, that would be a completely valid assumption, but I'm not sure how interesting that would be." Right, let's just run that one more time and see whether we can. Okay. Oh! there we go. He died straight away that time. He bumped into a lava block. But like I say, it still needs a bit more work. There we go. And it died again. Yeah, straight away. As I say, it still needs a bit more work in terms of the learning and actually getting processing on that. But I hope you enjoyed that. So thank you very much.